Okay, the general form of the rate law always takes the form of the rate equals K times the concentration of one reactant to some power and the concentration of the other reactant to some power. So to figure out what these powers are, we need to do, I call it table logic. Okay, so we need to use table logic to figure out what the powers are. I'm going to switch over to the chart on the book. Okay, so here's the chart on the book, and what I need to do is figure out a trial where I is being constant and a different trial, well, a set of trials where Z.12.26 is being constant, so that I can figure out what effect is each of these substances having on the rate. So I look at my I column, and the only two that are constant are trials 1 and trials 3. So comparing trials 1 and 3, I now look at the other substance. I see 0.04 was cut in half to 0.02. I also see 12.5 is cut in half to 6.25. Because this change is the same number, half and half, then I know that the exponent there is just 1, because anything to the first power is still the same thing. So I can go back to my rate law, and I can put K equals the concentration of Z.12.28, I think it's -2, is going to be to the first order, or power of 1. Now, if I look at the I data, we need trials where 1 and 2 are the same, and I see, we need trials where the Z.12.08 concentration is the same. So I see 0.04 to 0.04, and I see 0.08 to 0.04. So when it was cut in half here, the rate was also cut in half. So this reaction is also first order with respect to I. Okay, so that would be the equation, the general equation of the rate law for this reaction. Now I want to remind you, we haven't talked about why these numbers are 1. All we're doing now is using data to figure out these numbers. We don't really know yet what the order of the reaction means, but you can still do these problems without knowing it. The second question says, calculate the value of the rate constant for each experiment and an average rate for the rate constant. Okay, seems like a big waste of time to me just looking at it, because we're going to get the same number for each one. If you look at any of the trials, you can just use these numbers and substitute into the equation to solve for K, but you got to make sure that you give K with the correct units. So I'm going to take rate is 12.5 times 10 to the -6 equals K times the Z.2.04 and the I 0.08. And solving for K, I get that it is equal to 3.9 times 10 to the -3 liters per moles seconds. And I knew those were the units because the rate has to be in moles per liter second. And this is moles per liter. This is moles per liter. So the only way I'm going to get moles per liter seconds is if I get rid of one of these moles per liter and I divide by seconds. So it's going to be liters over moles times seconds. And that's going to cancel there and there, there and there. And I'm going to have moles per liter second. Oh, you could just barely see that. I got lucky. All right, thanks.